Welcome back, everyone. Let's get started.
I hate this.
I kind of hated making it. Well, this hopefully might, maybe, kind of, sort of, might make it a little easier. A student asked on the discussion forum yesterday how to enable debugging, enable assertions when running the code in Visual Studio Code. That kind of caught me off guard because I'm totally used to the command line. I thought, I'll just tell everyone to use -EA and it'll be fine. But I forgot that people, for very good reasons, like to press the play button and run their code in a graphical environment. So I did answer that question. You could see it in the discussion forum, but it's actually really hard to explain exactly what you have to do to enable assertions in VS Code. So I'm just going to do a quick demo of that and then follow along right now, of course. But then in the lecture recording, you could use that to help you set up assertions if you haven't already. So I have my assignment folder right here. Specifically, I'm in my A3Q3 folder. The same ideas would apply for A3Q2. And if I just run and debug it, I'll get that error message about how assertions need to be enabled. And none of the tests will actually do anything. We basically have to make it so VS Code will interpret our configuration as if we typed -EA. And to customize run and debug, we will create a launch.json file. This creates a launch.json file. And then you paste in something from a Stack Overflow post that I found. It's on Stack Overflow, so it's objectively correct. Via margs is set to enable assertions. Paste that in there, fix the commas, and then it should just work. Go back to test inventory because that's the file containing the code that you're actually executing. Press the play button. And then, if you've done your work correctly, you'll see all tests pass. If you haven't, you'll see a test failure, but either's better than no tests running at all. All right, happy fishing. Next up, we're going to finish up,
I have a problem with the description form, but I'm curious about this too. Someone asked, I don't remember that question answered, if you can use the internal linked list in the third question.
Yes. I answered that too, and the answer is yeah.
Okay, so when you say one thing, it's only for that question.
Only for that question.
Okay, that's good clarification.
In general, my reasoning for that is, as I've explained before, this course is about data structures, and even though you won't end up remaking any in the real world, implementing them yourself is a great way to learn about them. Question 3 isn't really about linked lists. It uses linked lists, but you have already proven your ability to write a linked list class in question 2. So on question 3, you can relax a little. You still have to implement your own hash table, but I no longer care about your ability to write a linked list class because you have to write your own in question 2. So what were we talking about on Monday? I think we're looking at worst case runtime for the binary search tree operations. We found that the insert and search operations both have a worst case runtime of big O of h, where h is the height of the tree. which basically means as one of those operations is traversing the tree, the worst it can do is traversing the entire tree. Now, what about delete? Turns out delete is also in big O of H, even if you're directly given a pointer to the node that you want to delete. That's because the delete operation involves searching for the node's successor, and the search for the successor might run into the worst case scenario for the search operation. So I guess you could make a better delete operation, a constant time one, that gives you a pointer to the node to delete and its successor, but you would still have to search for the successor, so you would just be taking O of H time somewhere else. You can't really get around this. The worst case runtime for delete is O of H. This is a pretty good conclusion for us wondering about the time complexity of binary search tree operations. Turns out the big three, insert, search, and delete, are all O of H. But H is sort of a emergent property of the graph, or of the tree. A tree doesn't I don't want to say it doesn't intrinsically have an H property, because it does. It's more like H doesn't really represent the size of the tree in a normal way. We much more often care about the number of items that are stored in a data structure, N. So in this tree, H is 1, 2, 3, and N is, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. It would be ideal if we could express these worst case runtimes in terms of N instead of H, because N better represents the size of the tree, the amount of space that it takes up in memory. So we're going to derive a rough formula for H in order to express those O of H operations in terms of N. And to start, we're going to think about what the maximum possible number of nodes in the tree is if a BST has height H. So I'm going to try to draw just the busiest possible BST that I could think of with a given height. So let's say H is 0. We'll start with that. 0 edges from the root to any given leaf, or to the farthest possible leaf, I mean. That's just one node. There's nothing I could do to improve upon this, because adding a child would increase its height. Same with giving this node a new parent. And adding a new disconnected node would make it not be a tree anymore. It would be two trees, but it wouldn't be a tree. Now what about H equals 1? The longest path from a root to a leaf is 1. So there could be a node here and a node there. Again, this is the largest possible tree I could ever make with height 1. I can't add any other nodes without increasing the height. I'm going to make a little table. So let's keep going for h equals 2 and 3. I'm going to increase the height while having as many nodes as possible simply by adding all possible children to all of the roots. No, to all of the leaves. I actually had 3 nodes back there. And then we'll do this again. So we started with 7 nodes. And we added, I think, 8. 1, 2, 3, 4, 6, 7, 8. We end up with, at most, 15 nodes. A pattern begins to emerge. The maximum n seems to be growing exponentially, like it's roughly doubling each time, but not quite. Seems like n is equal to, what? Something like this. Probably shouldn't write this down. I might be wrong. It's definitely an exponential function of some sort, but the really good info that you can trust is on the slides. What I'm doing right now is an illustration of the process of just looking at many different cases, trying to find a pattern, and guessing a formula based on that pattern. The trees that we were drawing in the previous slide are called perfect binary trees. There are a few different words for different ideas of binary trees with as many nodes as possible, and the definitions are very easy to confuse. For now, you only have one though. Just know for now that a tree with all of its rows full is called a perfect binary tree. Look at that, you can't improve it. Also worth noting is that if you number the rows from 0 to h, then each row j can hold up to 2 to the j nodes. Row 0 can hold 2 to the 0, which is 1 nodes. Row 2, 2 to the 1, 2 nodes. Row 3, 2 to the 3, 8 nodes. And row 4 can hold 16 nodes. So a nicer formula for the number of nodes in a perfect binary tree is as follows. The summation represents going through each rows, and then the 2 to the j represents, well, what we just saw. Each row j can hold 2 to the j nodes. So this is progress. Remember that n is sort of a more natural measure of the binary tree's size, and that we want to measure the complexity of the binary search tree's algorithms based on that natural notion of size n. So now we can express n in terms of h. That's a bit better. Our goal will be to express h in terms of n so that we could change O of h into something involving n. So how do you solve for a variable in an exponential function? How are we going to solve for h starting from 2 to the power of h plus 1 minus 1? Wait, is that exactly what I got on the slide? Yes. You use a logarithm. Some simple algebra later, and we get that h is the base 2 logarithm of n plus 1, which means that h is in big O of log n. I might have mentioned this before, not sure, but it is notable that we dropped the base of the log here. That's basically because the base of the log doesn't really make any difference in terms of asymptotic growth of a function, while something like n and n squared are two very different functions. N squared will grow way faster than n. Something like log base 2 versus log base 3 of n are basically the same. The notion of basically the same, of course, is formalized by the definitions we saw with constant multiples m and n naught and stuff. But I'm rambling at this point. The point here is that we don't have to say that it's in big O of log 2 of n because we don't really care about the difference that the base makes. And that finally gives us complexities for these functions in terms of n. The worst case time complexities of insert, search, and delete are big O of log n. Now that I know I'm saying this again and again, but it's important. Now that we've made it so the complexity of these operations isn't in terms of h, it's now in terms of n, we can more easily compare it to data structures that don't have an h, like a hash table. Remember that that one had average case time complexities of average case time complexities for its regular operations of O of 1. And a linked list had O of n for many of its operations. So we could see that binary search trees are kind of in between hash tables and linked lists in terms of performance. And remember from the very beginning of our discussion that binary search trees have the sort of memory flexibility of linked lists. So in your choice between a binary search tree, a hash table, and linked list, you have to consider the amount of memory you're able to take up and how much speed you want. Weigh those trade-offs with each other. Now, I'm about to ruin binary search trees because this O of log n is actually kind of misleading. It's true that O of log n is, oh, sorry. I hope your hand wasn't up for a very long time. What's your question?
Why doesn't it say best case there?
Best case where?
Just in bold.
Okay. Probably because the whole slide was meant to be best case. This worst case thing, I didn't really mention it, but I found the wording a bit weird. This was probably a typo that I didn't notice until now. It's true that O of log n is the worst case for a tree that looks nice, and then the notions of worst and best case can get kind of muddied from here because it's possible for the tree itself to have a worst case structure that makes it so the runtime of those algorithms gets a lot slower. Actually, I thought of a better way to explain it. Best case here refers to the structure of the tree. In this case, suppose the end nodes are arranged in a perfect binary tree. If the binary tree is perfect, then the worst case runtime for the algorithms is in big O of log n. So this is like the best possible worst case, which is cool because the next slide will talk about the worst possible best case. Because quite sadly, this is also a binary tree. If we insert values in ascending order, or descending order, I guess, the binary tree just kind of turns into a linked list. Like, start with 1, insert 2, 2 is greater than 1, so it's the right child. Insert 3 goes on the right, insert 4 goes on the right, keeps going. So if this happens, this is the worst case structure for the binary tree. And then the different cases of the algorithms we studied kind of just stop mattering. They're all going to be in O of n no matter what you do, because the data structure just sucks. So that's a bit of a bummer to end this week's material on, but luckily we're working ahead. And we're going to learn how to solve this problem and make it so the worst case time complexity is still not that bad in the previous best case of the data structure. This was meant as a review to get you warmed up on Monday, but we just learned about this. If the binary tree is perfect, then the worst case time complexity is O of log n. But if the binary tree is the most imperfect it could ever be, if it is reprehensible, then all the operations will be in big O of n. So we're going to learn about different types of trees. They'll actually stop being binary after a while, that avoid this worst case. You can insert the items in any order you want, and the tree will still be balanced. The path from a root to any leaf will still be relatively short. And before I go into exactly how you might keep a tree balanced, I'll talk about the quiz. I'm sort of making policy up as I go, I fully admit. But I'm thinking on weeks where we work ahead, the quiz is still only going to cover the material that was supposed to be from that week. Meaning that the quiz on Friday will contain material about binary search trees, but not about 2-3 trees, AVL trees, red-black trees, or B trees. So, as with previous weeks, it's Wednesday today, and I'm partway through making the quiz. One question is absolutely certain. The other question I'm going to make after I knew what we were going to cover in total in that week. There's definitely going to be a question about inserting a bunch of values into a binary tree, and the other will probably be about some other operation like delete. it might be a more mathematical question about the height and the relationship between h and n, but it's going to be about BSTs. I really like this bit. In order to maintain that the binary search tree, or just search tree in general, operations stay efficient, we need to force the tree to look like a tree and not a stick. I just like that a bit. This binary tree, this perfect one, we say that it's balanced because, well, the height is basically the same on each side of the tree, as opposed to this monstrosity where, in the case of the root, its right child has height 14-ish, and the left subtree has height 0. It's very unbalanced. We want our tree to stay balanced, so we're going to study what are called balanced search trees. 2-3 trees are going to be the focus of this/next week. And then there are a few more possible balanced trees. AVL trees we may or may not introduce in the course. Red-black trees and B trees won't be in this course, but it's worth mentioning that there are many more possibilities for how to solve the problem of a binary search tree degenerating into a linked list. So what's a 2-3 tree? Where did the 2 and the 3 come from? Well, our recursive, or those fun recursive definitions from before, turn out to be the best way to define a 2-3 tree. So a 2-3 of height 0 is just one node. So far, it's identical to a binary search tree. A 2-3 tree of height greater than 0 can be one of two shapes. One of the cases is a root node with 2 children, each of which is the root of a 2-3 tree with height h minus 1. So far, this is identical to a binary search tree. If we just stopped our definition at this slide, crossed out 2 and put 1, then we'd have a binary search tree. So what differentiates it? A 2-3 tree with height greater than 0 can also be a root node with 3 children, each of which is the root of a 2-3 tree with height h minus 1. So 2-3 trees aren't really binary anymore. You could kind of call them trinary, but that's maybe misleading because nodes could still have 2 children. 2-3 trees is a nice name. This definition probably isn't very inspiring. It's not anywhere near clear yet how this solves the problem of a binary search tree degenerating into a linked list, but it turns out it does. If a 2-3 tree has height h, then every branch of the tree will have the same length. The height will be constant everywhere. Oh, and of course, like the fact that this is balanced, I already said that it's unclear from the definition, but it's not even fully explained by the definition. Different things. We'll have to look at the algorithms used for insertion, searching, and deleting that will use the properties from the definition, and then those will really show us why 2-3 trees stay balanced. The nodes in a binary search tree have data that's organized in like almost the same way as the binary search tree property, but it's a bit different because now a node can have two values. And if it contains two values, call them D0 and D1, then they're ordered so that D0 is less than D1. They're in order. If a node contains one value, then it has, well, exactly two child nodes, I guess. I would say either 0 or 2 child nodes. So call the left and right subtrees TL and TR. And then TL and TR will obey the same rules as values in binary search trees. All of the nodes in the left subtree will be less than the node's value. And all the data in the right subtree will be greater than the node's value. Oh, and also I made that correction a few seconds ago saying that like, oh, I guess, well, actually, these, or if an internal node contains one value, then it has 2 or 0 child nodes. But no, an internal node is defined as not being a leaf. So if it has one value and it has children, then it has 2 children. If an internal node contains 2 values, then it has 3 child nodes. And the nodes are arranged according to a generalization of the binary search tree property. The data in the left subtree is less than the smaller of the 2 node values. The data in the middle subtree is in between the 2 node values. And the data in the right subtree is greater than both of the node values. A 2-3 tree with data that are organized in this manner is called a 2-3 search tree. That's kind of squabbling over definitions, I think. You're never going to use a 2-3 tree that isn't a 2-3 search tree. So here's an example of a 2-3 search tree. This tree has height 2 because the longest path, in fact, all paths, because it's balanced, all paths from the root to any leaf have 2 edges in them. Some nodes have 1 value and then either 2 or 0 children. Other nodes have 2 values and thus either 3 or 0 children. And in the case that a node has 2 values and 0 children, we see that everything in the left tree is less than either of them. Everything in the center tree is in between. Everything in the right tree is greater. Cool. This is going to get really complicated eventually, but the search operation should still be pretty familiar if you know what you're doing with binary trees. The search operation really follows the same rules as the binary search tree search operation, just with the rules a bit generalized to account for the possibility of there being 3 values. We're going to search the tree for the value 19. And before, we would check if 19 is less than or greater than the value in the root. But now there's a third case of it being in between, which is what happens. 19 is greater than 11, but less than 22. So we move down to the middle subtree. This node has just 1 value, so we go back to the rules that we used with binary search trees. 19 is greater than 18, so we move right. And 19 is one of the values, one of the two values in the next node. So we found it. This is the logic behind the search operation. You could kind of see this as really high-level pseudocode, but it's what we just went over. If the node contains one value, apply the same logic as a BST search. If a node contains two values, then either go to the left, middle, or right subtree, depending on whether the search key is less than, in between, or greater than the two values. And then a search ends when the key is found or we reach a null pointer without finding it. So if we wanted to search for, 100 in there, we would go right because it's greater than 22, go right because it's greater than 26, attempt to go right because it's greater than 30, end up at a null pointer and return some sort of failure value. This should be familiar so far. And this should get weird. The insert operation is kind of complicated, and the delete operation is very complicated because there are some properties that you have to preserve when you add a new node to a 2-3 search tree. So suppose we start from nothing and insert the value 1. The root node is now just one node with value 1. And then we're going to insert the value 2. We insert the 2 into the root node. In a binary search tree, you would have added a right child. But in a 2-3 tree, you always grow the current node before making any new nodes. Now what happens if we insert another value, 4? We do the same thing again, run a search for the value that we're inserting. In this case, it's really fast because there's only one node. And then we add the new value to the leaf we find in the search operation, keeping the values in ascending order. And now, at this point, the root node has 3 values, which isn't allowed in a 2-3 tree. So we're going to do a thing called splitting the node. So what's a split? I like to imagine these nodes as being like cells that undergo mitosis, and then boom, 2 cells. Or in this case, 3 cells, I guess. We're going to move the middle value up 1 row. It'll become the parent, and the 2 values that are left in the node will become its left and right children. It's going to look like this. The middle value goes up to become a new parent, and the extreme values move down to become new children. So let's insert a couple new values. We insert 11. 11 is greater than 2, greater than 4, and there are no further children. So we put 11 in the same node as 4. Insert 13. It ends up at the extreme right of the tree again. And we end up with a node that has 3 values in it, 4, 11, and 13. 3 values is too much for a 2-3 tree, so we move the we split up the node. 11 actually goes up and joins 2 at the root, and then 4 and 13 become the new middle and right child, respectively. Looks like this. Oh, wow. Next huge chunk of this lecture is just inserting stuff. Let's keep going, I guess. So let's add 18 and 19. Should maybe be seeing a pattern here. In this state, all of the leaves just have one value. So when we insert a new value, it just gets added to one of the leaves. If we add another value and it ends up in the same leaf, then we end up with a node with 3 values. So eventually 18 is going to be pushed up to the root, and then 13 and 19 are going to become children. But if you're doing an incredibly good job of following along, no worries if you're not. This should be setting off some alarm bells because this will not result in a valid 2-3 tree. Now the root has 3 values and 4 children, which violates our definition. So the splitting operation, algorithm, mechanism, I don't know, the splitting thingy that happens recursively. Sometimes when we split a node, it'll result in a valid 2-3 tree immediately. But sometimes when you split a node, it'll result in a parent node that has to be split once more. And now it's not completely clear how it should split. Clearly, the 11 should go up, form a new parent, but now its children have children, and we're not sure how to manage custody. The idea that we're going to use is for the left child to carry the 2 left children, and the right child to carry the 2 right children. I guess you could say the new left child has the left grandchildren, and the new right child has the new right grandchildren. And this is what the result will look like. Remember, we had previously a node with 2, 11, and 18. This turns into node 2, child of root 11, and node 18, child of the root node 11. And then 2 has the 2 leftmost children of the original 4, and the right node 18 has the 2 right children of the original 4. Yeah, this next bit, like I mentioned, is just adding a few more values. We're building up to a neat reveal, and I want to get to that before the class is over. So I'm going to rush through this example a little bit. You should definitely take the time to do it on your own. Just start from this slide and then do it blindly on paper without peeking at the future slide, and then check your work. So 22, because of the binary search tree property, it's going to end up in here. Yeah. Now we insert 25. The 25 will get added to this rightmost node again. We end up with a node that has 3 values, so we need to split it. 22 will join 18 in that node, and then the joint 1822 node will have child nodes 19 and 25. Like that. Adding 26 is simple enough. It just joins the node containing 25. Adding 27 causes a recursive split. We're going to bring 26 up into the parent, make a new node that has 3 values and 4 children, and then split that up again, causing the new root to have 3 values and 2 children, and all of its descendants, I believe, to have 1 value and 2 children. So this is the result of the first split. Now, this node has 3 values and 4 children. We split it. And we end up with the tree being just as predicted. So now we're at that reveal that I mentioned. So observe, the search tree is balanced. If you want to insert a new value anywhere in the tree, or if you want to search for something or delete something, these operation will take at most 1, 2 operations, like traversals through an edge. But recall, we inserted items in the order. Actually, I'm just going to scroll up for this. So we started by inserting 1, and then we inserted 2, and then we inserted 4. What did we do next? 11, 13. Oh no, I've ran out of space because my binary tree sucks. If we inserted items in the exact same order into a binary search tree, that would have been completely unbalanced because they were inserted in ascending order. So this was actually a demonstration of how 2-3 trees retain balance. We'll talk about 2-3 trees more on Friday, but this is the end of this lecture, so good luck on the quiz, and I'll see you all on Friday.